My name is Ekechi Nzewi, a student from Georgia Institute of Technology, and I am here to present my project, Leaf Size Analysis with Computer Vision, which was done under my 2023 RISC Scholarship and the mentorship of Dr. George Cantor. Background: Plant phenotyping involves the characterization of crops. Characterization aids in the decision-making of plant breeders when selecting variants with the best features for future agricultural efforts. With the use of computer vision, breeders can estimate the size of leaves, which can in turn inform them about the growth of crops, or conversely, the growth of unnecessary weeds around their crops. The goal of this project was to build a system that allows us to capture images of leaves and analyze their sizes in real time. This is done through color segmentation and quantifying which pixels in frame belong to the leaves and how many of them are there, which can give us an idea of the size. The system overview. Color segmentation was what we used to detect which pixels in a frame belong to the leaves. For this, we trained three SVM models to compare their performance. The models represented a color space, which were either HSB, RGB, or the LAB color space. Once the models had been trained, we put it into the system and ran it. And what it does is essentially it takes a frame and then generates a mask based off where in the frame it identifies what it thinks are leaves. And then this mask is overlaid onto the original image and displayed back to the user. This cycle continues running in almost real time to give the user an estimate of how the leaves are and where they are and if they enter the frame or leave the frame. The results. All three models showed comparable performance when it came to detecting leaves in adequate lighting conditions. However, the HSB and LAB models often detected false positives in the form of shadows for the HSB and brighter objects for the LAB. This can be seen in the image on the right, where the flashlight has a little speck of red, which indicates the model thought something around this area was a leaf. And for the LAB, in the top left, there's a speck of red where the table is brighter. For the RGB, however, it only ever detected the leaves which were red and nothing else in the frame was red. And out of the three models, HSV performed the worst across the board, while the RGB and LAB, depending on the lighting conditions, could give similar, if not the same result. For future work, we would like to improve the quality of the model because time constraints did not allow us to fully flesh out the model to be as robust as it could be. Thus, that is a potential next step. In addition, once we have a more robust model, the system can remain the same, but we could change out what it is we're detecting. We could move from leaves to plants to other things that could be useful depending on the context. Also, the time constraint did not allow us to display the size of the pixels in frame. So all it shows right now is how many pixels they are with the 8 of the red math, but it doesn't tell us the size, it doesn't quantify it for us. So that is a further thing to improve upon. And lastly, our camera was prone to overexposing, which often muddied the results we were getting. So it would be better to look into a new and improved camera system, which would hopefully also speed up the process and help us achieve real-time performance. This work was sponsored in part by the CMU Robotics Institute Summer Scholar Program. And I would like to thank Dr. George Cantor and Abhisesh Silwal for mentoring and supporting me throughout all the phases of this project. And I would also like to thank Rachel Bursing and John Dolan for making this project possible for me. Thank you.